You guys kind of remember that from Tuesday? Okay, cool. So we're talking Jules' Law has something to do with energy, right? And that makes sense because at the end of the day, right, when electrons meet resistance, heat energy gets transferred, right? So what Jules' Law essentially states is 1 joule of energy, 1 joule of energy is transferred, I guess, emitted, whatever, is transmitted into the human body, right? When 1 amp of current, right, 1 amp of current flows through 1 ohm of resistance for 1 second. All right, so that's Jules' Law. All right, so taking all this stuff we talked about earlier today, we can kind of condense it and say, if I have 1 amp of current flowing through 1 ohm of resistance for 1 second, that situation will deliver 1 joule of energy into the body, or whatever it happens to be flowing through, right? Okay, cool. And then just to remind you, when we talk about things that conduct current, so if I'm talking about something called a conductor, that must mean that the resistance is low, right? So to conduct electrical current, you want to have low resistance. You're a more effective conductor. If you have high resistance, right, that tends to be called an insulator. You guys okay with that there? Now let me ask you a question. Is the human body a particularly good conductor of electricity, all things considered?
Yes.
Not really. We're not the greatest conductor of electricity. The skin's not the best, right? So when you have a situation where substantial amounts of electricity gets conducted through the body, what does that mean? What does that mean? If someone has been exposed to electricity and it actually went through their body, it actually conducted through their body, is this a benign situation? No, right? Because under ordinary circumstances, right, I could put my hand on this electrical outlet here and nothing's happening, right? And there's electricity right there. There's 110 volts of potential energy just right there, right? And nothing's happening. Now, if I were to stick something conductive into that and directly interface with it, something would probably happen, wouldn't it? Right?
I don't know. Should we test it?
Yeah, let's not. Let's not pretend we did. So what I'm saying is, if somebody has a potential electrical injury, a unique situation has occurred. Something has to have occurred and able to get electrons to flow through their body, right? And that generally means that they've been exposed to unnatural situations, or situations that we don't normally run into as human beings. And so the general rule of thumb is any suspected electrical injury is a critical burn until proven otherwise. Any suspected electrical injury is critical. This is a critical patient until proven otherwise. All right? Is that, you guys okay there? Okay. Now, when talking about electrical injuries, we can talk about voltage first of all. But remember, voltage is not the be-all, end-all, right? Because you can have super high voltage, but if that voltage is behind something with a significant amount of resistance, well, then the current's going to be rather small. But if a human being gets directly exposed to a low voltage situation, and that generally is less than 1,000 volts. So if you directly expose someone to a low voltage situation, what happens? Well, what happens is, if a current ends up going through your body, because we are not great conductors, all things considered, the current will go the path of least resistance through the body. Which means that that current will tend to follow structures in our body that have a very low resistance. Nerves, blood vessels, and muscles, right? And so the path that it may take through your body may be very convoluted. If I grab a low voltage source, right, it may not go, let's say I grab a low voltage source and then I grab some other metallic object as a ground. You would think that it would just go right through your arms, right? Because that's the shortest path. Maybe not, because it may just travel through a nerve and then go through your brain, down your spinal cord and into the ground, and that may be the path of least resistance, right? Now, high voltage injuries, right? So 1,000 volts or more, right? This tends to go the shortest path, right? So low voltages tend to path of least resistance through the body. High voltages tend to be the shortest path. So far, so good. All right, there are other types when we talk about the current. We talk about how the current flows. There are two general ways that current can flow. Current can flow in a constant, continuous direction, and we call that direct current, DC. Right, so that's like your standard battery. You put a battery into something and electrons flow out of that battery through a circuit, right, and the kinetic energy is used to do work. That's a direct current situation. Lightning is also a direct current injury, right? However, exposure to standard electrical systems in industry and in the house tend to be what we call AC, or alternating current, and that is to say that the direction of the current alternates, and it tends to cycle on what's called a sine wave, right? Typically about 60 hertz or 60 cycles a second is when it alternates.
Here in the States.
Yeah, at least here in the United States, right? Now, alternating current injuries, because that current is alternating, its motion is moving like this, and the reason that we tend to use AC currents in typical applications is they can actually travel long distances very efficiently, and so that's why we tend to use it in industry. But alternating current tends to cause muscle spasms, right? And it tends to cause VFib, whereas direct current tends to cause muscle paralysis and asystole. Right, so lightning strikes, almost done, Art.
Okay.
Just a couple more minutes and I'll be done. So lightning if you get exposed to a high voltage lightning injury, that's direct current, that tends to paralyze your muscles, depolarize and paralyze your muscles, and it tends to stop your heart. Right? So these patients tend to present with respiratory arrest, asystolic cardiac arrest. Right? So think of lightning injuries. Now, if you have a massive number of lightning injured patients, aside from all the scene safety considerations, how would we approach that situation? Or would we approach it any differently than standard triage?
Well, I mean, is the lightning still there?
So I already told you guys, right? I already said we are going to take the scene safety component out, right? Right, so we've taken that out of this scenario, and we're just going to focus on, I have a bunch of people who have been exposed to lightning, they're all appear critical. How do we triage them any different than we would do the standard start triage?
I feel like there's extenuating circumstances.
Yes, we would triage them differently. We would do what's called reverse triage. Right? Because with standard triage, the people that aren't breathing and the people that do not appear to have a heartbeat are black, right? But when it comes to lightning injury and these direct current injuries, right, these are the patients that need our care the most, right? Because if we can do CPR, we can breathe for them, right? They tend to do okay, right? They are apneic because their diaphragm's paralyzed from the direct current injury, right? So if we can do CPR on them, we can breathe for them, they do all right. So the people that are not breathing are going to take precedent in that kind of situation, right? So it's kind of what we call reverse triage.
Black tags or red.
Yeah, they become the reds in that case, right? Because there's a really good chance that they're a salvageable patient, right? So do not give up on a lightning strike patient who appears to be maybe they're asystolic or PEA and they're not breathing, right? Typically, that's a write-off patient, right? That's someone who's
Write-off.
we're writing them off in essence, right? They've been in VFib forever, we've coded them for a long time, okay, let's call this thing. Not necessarily the case of lightning injuries. Now, alternating current injuries, high tension power lines and things like that, these tend to cause severe muscle contractions, right? Not as opposed to muscle paralysis, and they tend to cause VFib, right? So these kinds of injuries tend to present very differently than, say, lightning injuries and your standard electrical injuries. All right?
Can't those light you up too? Like burn you?
What's that?
Like from the heat of it?
Both of them can, yeah. And that's another concept. This is a common way that people actually get injured through what's called an arc or a flash burn, where if the voltage is high enough, the voltage can overcome the resistance and electricity could arc through the air into me, right? That's what we mean by arcing. Generally, it doesn't do that. But if the voltage is high enough, like lightning, right? If lightning is close enough to you, that's such a high voltage situation that the voltage will overcome the resistance of the atmosphere and the resistance of the human body. Or if you're close enough to a high tension power line, say, you could get arcing there as well. Yeah, and that arcing, right, since there's so much resistance in the atmosphere and resistance of like sweat and fluids on your body, or even your clothes, sometimes they will combust due to that transfer of thermal energy, right? And so patients can actually get burned on the outside of their body as well as the inside of their body due to the current that goes through, right? And they get arcing on their skin. With lightning injuries, it's not uncommon for the sweat on your skin to vaporize, and we talked about that in environmental already, right? The fern pattern that you get with lightning injuries. But yeah, like burning of clothes, or if somebody's holding a tool, sometimes the tool can vaporize and it'll actually produce like a shadow burn on their body, right? So lots of different things can happen with these electrical injuries, and they're all critical patients until proven otherwise. And because muscles tend to be involved, because muscles are more conductive than other types of tissues in the body, things like compartment syndrome, rhabdomyolysis, life-threatening hyperkalemia, dysrhythmias, renal failure, all those things tend to be more common with electrical injuries. So does that kind of make sense? And obviously, there are multiple scene safety considerations, right? When it comes to lightning, there are some principles we talked about in the book. You don't be the tallest object around, and so on and so forth. If it comes to industrial electrical injuries, right, you got to think about, well, how do I negate the source of the voltage and current, right? How do I shut the power off? Those kinds of things. How do I actually access a patient safely? Okay, I'm going to cut it off there because Art's going to come in and start orientation for you guys.